topic of valve trim. I'm going to discuss what it is and why it matters to good control. Essentially what we're looking at is the shape of the plug as it sits down in the seat and how that shape of that plug changes the water flow with respect to stroking the valve. Let's take a look. There are three common valve plug shapes: quick opening, linear, and equal percentage. As we stroke the valve stem, we're actually moving one of those three valve plug shapes in and out of the seat of the valve, therefore changing the water flow. Let's take a look at the first one, quick opening. You see it's a very shallow plug there. When we look at the diagram over here, we see flow over on the left. We see how we're stroking the valve down on the bottom. Let's take a look at just the quick opening first. As we stroke the valve 25% of its lift, we don't get 25% of our water flow. We get nearly 75% of our water flow. You can see why we call it quick opening. When we stroke the valve so that you would think it would be halfway open, so we're at 50% of our stem lift, we're now up here at maybe 85 or 90% of our water flow already. When we stroke it to 75% of its lift, we're close to 100% of its flow. You can see why it's called quick opening. So you can imagine the tremendous amount of water flow you'd get through a heating or cooling valve with just a small signal going to the actuator on that valve. The linear is more of a cone-shaped plug. On this one, when we stroke the valve 25% of its lift, we get 25% of our water flow. When we stroke it halfway open, or 50% of its stroke, we get 50% of our water flow, and at 75% of its stroke, we get 75% of the flow. So you can see why it's called linear. Let's hold that one for a moment, and let's look at this one, which is more of a heavy set sized plug. On this one, called equal percentage, when we stroke it 25% of its lift, you can see on this sketch we are getting maybe 8 or 6 or 8% of its flow. When we stroke it halfway open, we're maybe at 12% of our flow rate. And when we stroke it 75% of its lift, it looks like we're looking at about 30% of its flow. And then after that, as we stroke it farther, the flow takes off quite rapidly. We know that a quick opening valve is going to be more like a solenoid valve. That quick opening valve, if you give it a small signal from the controller to the actuator, you're going to get a tremendous amount of flow and overshoot the temperature you're trying to get out of that heating or that cooling coil. If you use a linear, one would think that that would be the logical choice, but it turns out it's not. You don't want linear either. You're going to have a very difficult to impossible time getting that loop tuned if you're using a linear plug. It's a surprise, isn't it? In reality, what we really want is we want the equal percentage plug, the one that looks pretty slow to react when you signal that valve to move and to start to stroke its stem. So why is it that the equal percentage is the preferred valve style? Well, let's take a look at that. To illustrate why a linear or a quick opening valve stem shape or plug shape is not going to work for us to have good control, let's take a look at an example here. I have a heating coil here, and we're going to pass some hot water through this heating coil. So we have a valve in here, and we're going to be passing some air across the heating coil, so we're in the process of using some hot water to heat some air. For this illustration, I'm going to take and put 1 pound of water through the heating coil. Notice I said 1 pound of water, not 1 gallon. And the specific heat of water is 1. It takes 1 BTU to change the temperature of 1 pound of water by 1 degree Fahrenheit. You may notice that that is the actual definition of a BTU. A BTU is the amount of heat it takes to change the temperature of 1 pound of water by 1 degree. We'll call it the specific heat of water also. Every substance has a different specific heat. The specific heat is the amount of heat it takes to change the temperature of 1 pound of that substance by 1 degree Fahrenheit. Based upon the definition of BTU, the specific heat of water is 1, simply by definition. We're going to pass exactly 1 pound of water through this coil, and I'm going to let the temperature change by only 1 degree. So whatever the temperature enters the coil, it's going to leave 1 degree cooler. So when we're cooling off the 1 pound of water by 1 degree, that means this heat was given up. This 1 BTU was given up from the water, and it's going to be going into the air. So consequently, we're adding 1 BTU to an air supply that we're putting across the coil. We're going to pass 1 pound of air in our example across the coil. Well, the specific heat of air is not 1, that's specific heat of water. Specific heat of air is 0.24, about a quarter of a BTU. We're going to be losing 1 BTU of heat out of the water, and that 1 BTU is going to be put into my 1 pound of air. Since specific heat of water is 0.24, about a quarter of a BTU, what we're going to be doing here is adding 1 full BTU to the air. With the specific heat of air being about a quarter of a BTU, that means the temperature of the air is going to increase by 4 degrees. So this temperature goes up 4 degrees Fahrenheit. As you can see, a small change in water flow causes a very large change in air temperature. We've got a 4-to-1 ratio there. If this were a linear valve plug, that's exactly what would happen. It would be very difficult to control that and very difficult to get that loop tuned. As it turns out, an equal percentage valve plug, the shape that we looked at a little earlier, will offset this 4-to-1 relationship and turn a small change in water flow into a linear change in temperature between the water and the air. We want a linear heat transfer process, and so in order to make what is a 4-to-1 ratio into a linear process, it turns out that the plug shape of an equal percentage valve plug will do that for us. And that's why we don't use a linear plug, and it would be even worse if we used the quick opening, wouldn't it? We want an equal percentage plug in all our valves where we're heating or cooling with water, and then we'll be able to get the loop tuned properly.